Hello my dear student, welcome to EPG Pathshala. I am Anchal Srivastava from Department of Physics, Banaras Hindu University, BHU. Today we are going to talk on the module titled Introduction, Synthesis and Characterization of Transition Metal Dichalcogenides under the paper Nanoscience and Technology 2. After completing this module, my dear student, you are able to learn the following things. You will learn about the 2D material, which is two-dimensional material, transition metal dichalcogenide, known as TMDs, which is an alternative material of 2D graphene. You will learn several synthesis techniques such as mechanical exfoliation, liquid phase exfoliation, CVD techniques for growing TMDs. You will learn the chemical vapor deposition technique for the large area growth of graphene. You will also learn the different characterization techniques for confirmation of the presence of number of layer synthesized for this two-dimensional TMDs. As you know, graphene, which being fundamentally and technologically interesting for variety of application, is chemically inert and can only be made active by functionalization with the desired molecules, which in turn results in the loss of some of the exotic properties. In contrast, the single-layered two-dimensional transition metal dichalcogenides, whose generalized formula is MX2, where M is the transition metal of group 4 to 10 and X is a chalcogen, exhibit versatile chemistry. TMDs with the chemical formula MX2, where X may be sulfur, selenium or tellurium, M is the transition metal, represent a particularly interesting class of 2D materials comprising both semiconductors and metals. For example, MOS2, MOSE2, WS2, WSE2 were shown to undergo a transition from indirect to direct band gap material when their thickness is thinned down to a single layer. Together with their strong interaction with light and relatively high charge carrier mobility, this has opened up the possibility of using few layer TMDs in a range of applications including ultra thin field effect transistor, photodetectors, light emitting diodes and solar cells. To date, optoelectronic research in monolayer TMDs has mainly focused on the MO and W based compound, which has optical band gap in the range of 1.6 to 2 electron volt. The behaviors of TMDs are varied, ranging from insulating to semiconducting, to truly metallic to superconducting. Reducing the stacking of TMDs to atomic layers lead to a new characteristics induced by quantum confinement effects. I want to discuss the molecular structure of transition metal dichalcogenides, which is known as TMDs. Many TMDs crystallize graphitic-like layered structure that leads to strong anisotropy in their electrical, chemical, mechanical and thermal properties. Group 4 to 7 in periodic table, TMDs are predominantly layered, whereas some of the group from 8 to 10 TMDs are commonly found in non-layered structure. For example, layered structure of MOS2, which is shown in figure, each layer typically has a thickness of 6 to 7 angstrom, which consists of a hexagonally packed layer of metal atom sandwiched between two layers of chalcogen atom, in this case sulfur. The interlayer MX bond are predominantly covalent in nature, whereas the sandwich layers are coupled by weak van der Waals forces, thus allowing the crystal to readily cleave along the layer surface. As suggested, like graphene, single layers of TMDs are stabilized by development of ripple structure. The metal atom provides 4 electrons to fill the bonding state of TMDs, such that the oxidation state of metal M and chalcogen X atoms are +4 and -2 respectively. The lone pair electrons of the chalcogen atoms terminate the surface of layers, and the absence of dangling bonds renders those layers stable against reaction with environmental species. M bond length varies between 3.15 angstrom and 4.03 angstrom depending on the size of the metal and chalcogen ions. The metal coordination of layered TMDs can be either trigonal prismatic or trigonal antiprismatic. If we see from the top monolayer of MOS2 having trigonal prismatic polymorph looks like hexagon with adjacent metal and chalcogen atom, and monolayer of MOS2 having trigonal antiprismatic polymorph looks like two interpenetrating hexagons. So, from here we can say that TMDs are layered material. One metal atom M is sandwiched between two chalcogen atoms. Weak van der Waals forces exist between two adjacent layers. Due to the presence of weak van der Waals forces, bulk TMD could be exfoliated easily. From top 2H phase looks like hexagon with the alternate metal and chalcogen atoms, and 1T phase looks like two interpenetrating hexagon. General formula of TMDs are MX2, where M is the transition metal like molybdenum, tungsten, etc., and X is the chalcogen where sulfur, cerium, and tellurium. I want to discuss electronic structure of TMDs, especially in case of WS2. Atomically thin sheets of MOS2 or WS2 consisting of a single to a few monolayer were recently found to exhibit a set of unusual properties associated with its two-dimensional structure and high crystal quality, triggering significant research interest. Geometrical confinement effect in exfoliated sheets of layered material lead to significant evolution of energy dispersion with decreasing layer thickness. Tungsten disulfide WS2 was recently found to exhibit indirect to direct gap transition when the thickness is reduced to single monolayer. This leads to remarkable enhancement in the photoluminescence efficiency, which opens up a new opportunities for the optoelectronic application of the material. Multilayered MOS2, WS2, etc. are indirect band gap material when these materials are thinned down to a single atomic layer, one metal layer sandwiched between two chalcogen layers. These materials converts into direct band from indirect one. This has been shown in figure, monolayer showing direct band gap band behavior at K point, while quarter layer shows indirect band nature in the figure. I want to discuss the synthesis of TMDs. To realize the application of TMDs, a consistent, reliable, simple and inexpensive method of growing high quality, uniform and continuous single and few layer of TMDs film is the present need. Two-dimensional TMDs can be fabricated using two types of approach similar to graphene, such as top-down approach, where the bulk form of are exfoliated into a few layer structure and monolayer, and the bottom-up approach using growth method such that chemical vapor deposition or molecular epitaxy. Various synthesis process for obtaining mono and few layers TMG has been shown in figure, showing the mechanical exfoliation, which is figure A, the most efficient way to produce the cleanest, highly crystalline and atomically thin nanosheet of layered material. In a typical mechanical exfoliation process, appropriate thin TMDs crystals are first peeled off from the bulk crystal by using an adhesive Scotch tape. This is the same method which has been used by Gaim and Novoselov to find single layer graphene from graphite. These freshly cleaved thin crystals on the Scotch tape are brought into contact with the target substrate and rubbed to further cleave them. After the Scotch tape is removed, single layer and multi-layer TMDs nanosheets are left on the substrate. While this method produces single crystal flakes of high purity and cleanliness that are suitable for fundamental research and characterization and fabrication of individual devices, but it is not scalable and does not allow systematic control of flake thickness and size. Therefore, this technique is not feasible for large-scale production of TMDs monolayer for technological application. The second method is liquid phase exfoliation shown in figure B. Liquid exfoliation methods are likely to be better suited for fundamental and proof of concept demonstration in application, where large quantities of materials are required, such as electrochemical energy storage, catalysis, sensing, or filler for composites, etc. The nanosheets were dispersed by sonication in the aqueous solution of the surfactant sodium cholate, which coats the sheet, preventing their reaggregation. These direct sonication techniques rely on the solvent or surfactant to overcome the cohesive energy between neighboring layers, which means the solvent must be chosen to have surface energy that are comparable to those of the material. The key challenge of this method is to enhance the yield of a single layer as opposed to the few layers, and to maintain the lateral dimension of the exfoliation sheet, because generally they fold and make few layers or wrinkles produced in that. The yield of this method is very high. Although the yield of lithium intercalation method for obtaining single layer TMDs is nearly 100%, some challenge remains. The first is that the experiment is carried out at high temperature, for example 100 degrees Celsius, for long duration, example 3 days. Also, the lithium intercalation must be carefully controlled to obtain the complete exfoliation while preventing the formation of metal nanoparticles and precipitating of Li2S. Another method is dip coating, which has been shown in figure C. In this case, the substrate is dip coated in the salt of transition metal and sulfurized in the presence of sulfur atmosphere. But in this case, sulfurization is not uniform and quality is not good too. Therefore, the second widely accepted approach is the bottom-up approach. The mechanical and liquid phase exfoliation process are both top-down process. Effort has been made since the beginning of graphene research to produce graphene in a bottom-up process state. The aim is to produce large single crystal of TMDs on substrate suitable for further study in a process scalable for commercial use. The mechanical and liquid phase exfoliation processes both fail to achieve this. So, due to the advantage of chemical vapor deposition growth on top of other existing technique, I will discuss the CVD synthesis in detail in my next slide. Chemical vapor deposition of graphene on copper has been a major breakthrough that has enabled the preparation of large area graphene. Very recently, synthesis of large area ultra thin MOS2 layer using CVD has been demonstrated using several approaches, which is clearly shown here in the figure. Most of the current CVD research has focused on MOS2. So I will introduce the details of MOS2 growth by chemical vapor deposition technique. A large area MOS2 monolayer flakes using the gas phase reaction of oxide, which is MOO3, and sulfur powder will be used. The process is shown in the figure, just we have shown in the previous slide. The CVD setup consists of 3-zone CVD furnace. The substrate will be used, it may be of silicon dioxide, sapphire or quartz, on which TMDs is to be grown, is kept in the 3rd zone in downstream at lower temperature. The precursor, such as MOO3, is kept at higher temperature of around 800 degrees Celsius in the middle zone, and sulfur is kept in the upper stream zone at lower temperature of around 200 degrees Celsius. The growth process includes evacuation of reaction chamber using rotary pump and backfilled with inert gas like nitrogen, argon. In this way, reaction takes place at atmospheric pressure. Precursors are transported into growth zone using carrier gas such as argon, hydrogen. Optimization of temperature, pressure, precursor amount, growth time, and cleaning of substrate is the most important parameters which one should always care for getting good quality monolayer growth of TMDs. Now, after the growth of these TMDs, further characterization will be needed to confirm the presence of monolayer TMDs. I want to discuss the optical microscopy characterization of MOS2 TMDs. Optical microscopy is initially the most powerful high throughput method for initially identify single and multi-layered flakes. Dielectric coated silicon dioxide substrate are the most common substrate used to visualize and locate the single and few layers MOS2 shown in figure A to F in this case. The color of the dielectric coated vapor depends on an interference effect from reflection of the two surfaces of the dielectrics. Single and few layer flakes on the surface of dielectric modify the interference and created a color contrast between the flakes and the substrate. In figure from A to M, color optical image of 1 layer to 15 layer of MOS2 on 300 nanometer silicon dioxide silicon substrate has been shown. The scale bar are 5 micrometer for an image 1 to L and 10 micrometer for image M. I will going to explain the Raman characterization of this TMD sample. Raman spectroscopy is a useful method for fingerprinting a material and layer dependent changes of the vibrational structure. When varying the layer number between bulk, few and single layer, the Raman spectra differs in spectral width and intensity due to the differing interlayer interactions. Raman scattering, a spectrum of 2H MOS2 single crystal has been shown in figure. There are 4 first order Raman active modes in MOS2. All of the first order bands are a result of vibrational mode within the SMOS layer, except from the E2G 32 cm inverse band, which is due to the vibration of the adjoining rigid layers. The A1G mode at 407 cm inverse is an intra-layer mode involving the motion of sulfur atom along the C-axis, which is clearly shown in figure. The E2G1 mode at 383 cm inverse is an intra-layer vibrational mode involving motion of MO plus sulfur atom in the basal plane. The peak at 286 cm inverse with weak intensity and E1G symmetry is observed, which involves sulfur atom in the basal plane. In addition, a rigid layer mode E2 at 32 cm inverse is present, which is of interlayer type involving rigid motion of neighboring layers in antiphase. I will discuss in detail the characterization of MOS2 using atomic force microscopy. The thickness of layers can be figured out, as well as the number of layers can be figured out using atomic force microscope. Atomic force microscope, abbreviated as AFM, is a powerful technique to determine layer thickness, which is shown in figure in detail with a precision of 5%. However, discrepancy arises from differences interactions of the tip with the sample and substrate. For example, the thickness of a single layer can be better determined by measuring the height of the second layer on a first layer rather than the height between a single layer and the substrate, because in the former the tri-player interactions are constant. To control these differences and obtain the most accurate height profile of single layer, one must first optimize the tip surface distance to exclude any hysteretic artifacts. AFM images and line profile of different TMDs on silicon dioxide silicon substrate has been shown in figure. Height differences for various TMDs is different due to the atomic size and bond length present in the material. Photoluminescence, which is known as PL, and high quantum yield of light emission of CVD grown WS2 monolayer. The first figure shows the PL spectrum of the corresponding color point shows in figure B. B to D is the PL images of the peak integrated intensity, position and width respectively. E, G and I are the optical images of mechanically exfoliated MOS2, which is one can call MCMOS2, and WS2 monolayer and CVD grown WS2 monolayer. F, H, J, the corresponding fluorescence images of the sample shown in E, G and I. The bright fluorescent images indicates the ultra high quantum yield of direct band gap light emission from CVD grown WS2 monolayer. K will show the PL spectrum of CVD WS2 monolayer excited by 457 nanometer laser. Individual monolayers of metal dichalcogenides are atomically thin two-dimensional crystal with attractive physical properties different from their bulk layered counterparts. Here we describe the strong room temperature photoluminescence. Bulk WS2 does not present PL due to its indirect band gap nature. The edges of these monolayers exhibit PL signals with extraordinary intensity, around 25 times stronger than platelets center. The structure and composition of the platelets edges appear to be critical for the PL enhancement effect. A strong PL is obtained only when monolayer is there. This means one can also confirm the presence of monolayer by direct observation of a synthesized sample in fluorescence microscope. So student, let us summarize what we have learned in this module. TMDs are represented as MX2, where M stands for metal ion atom and X stands for chalcogen atoms. TMDs such as MOS2, WS2 are layered in nature. Bulk MOS2, WS2 are indirect band gap material, but when these are thinned down to atomic layer, these materials are converted into direct band gap materials. There are several synthesis techniques for 2D growth, such as mechanical exfoliation, chemical exfoliation, etc. However, CVD techniques is the best suited technique for large area, good quality growth of such materials. Monolayer of MOS2 and WS2 gives a strong red emission under exposure of green light. Thank you.